I'm going to spend this lesson and last lesson, the final lesson of the day, on it. I don't know about you, I'm remembering, number one, when I did radian measure at the end of year 10, and number two, all the times I've taught radian measure, you guys know how it's crammed at the end of the year, and you've got all four of these weirdo topics that are really hard to understand, right? All of you are from different classes, right? But I don't know about you, most people, I think, feel quite rushed as they go through radian measure. And you're just trying to wrap your brain around this idea of, okay, why should we have this form of measurement for angles? How do you use it for circles and cones and sectors and blah, 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 right? So I'm sort of going to treat this lesson, as a fresh introduction to the topic, okay? So then we can actually get into the practicalities of using all of these rules for measuring things which are sort of round and circular, okay? So here's my first question to you, and it's going to lead into what this weird diagram is. I wonder what it looks like actually to you, because I have a very clear picture in my head of what it is, but anyway. Why a new way of measuring angles? Why a new, I mean, we've been using degrees for like 4 and whatever years, or longer than that, I suppose, if you were doing it from primary school. We've been using degrees for quite a while, and we've been quite happy with them, right? So why do we have to go to all this trouble of introducing a new way of measuring angles? Okay, that's my question, right? Now, and especially because you have to deal with this weird pi business, like at least you've got whole numbers over here, okay? So in order to answer that question, why a new way of measuring angles, I want to pose a question before that, which is, why the old way? Why is it that we take a revolution, right, and we divide it into 360 degrees? Where does that come from? Anyone got any ideas? Why 360? 360. Circumference? Circumference to arc? Okay, yeah, so we're talking about circles here. Good, that's a step in the right direction. You might think it has to do with something to do with ratios in a circle. Okay, because circles are where we would get angles from, right? They're these kinds of shapes, right? However, even though I think we're on the right track there, it doesn't answer the question why 360. Why not, if you're a European engineer, why not use these? Why not break it up into a sort of decimal number? On your calculator, you've got degrees, radians, and gradients, which divide a revolution into 400 of them. So why not that? That seems like a better number to use. It's metric, it's decimal. Why 360? 360. Any other suggestions? Yeah, Justin?
Just divisible by a lot of numbers.
Good. 360 is no ordinary number, right? How many factors does 360 have? A lot. Let's see. 1, 2, 3, 4, 5, 6. 7's a bit of a pain, admittedly, but is it divisible by 8?
Yeah.
Yes. It's divisible by 9, 10, not 11, 12. You can keep going from there, right? That's pretty good, right? Like, as numbers go, okay? certainly better than if you picked like 351. It's like, okay, I can't divide that into anything. So, alright, so it's convenient. It's convenient if you want to break things up into sections, which with circles I suppose we sometimes do. But apart from that, can you come up with any other reasons? Now, I will tell you who came up with 360. It's a very old number. Ancient civilizations came up with it. But it was not just anyone in those ancient civilizations. It was... Does anyone know?
A Greek person. Romans.
The Greeks, the Minoans.
A whole variety of societies have used the same 360. Different cultures. But it was always the same people within those cultures who came up with the 360. And the answer was, not who you'd think, it was... It was the sailors. Always the sailors. Now, what do sailors have to do with this diagram? Okay, you're out at sea, you're on a boat, okay? And if you want to know where you are, as a sailor you have a problem that normal, like a horse rider or someone who's just walking along doesn't have this problem. You look around and you're like, where am I? And you're surrounded by what kind of landmarks? Nothing, because there's no land to have landmarks, right? So you've just got water around you, okay? But you do have something. You do have something. It's not around you. It's above you, right? So sailors all knew, okay, we can look at the stars, and that gives us a general idea of where we are, because the stars are quite static. Like, you look at them, and you're like, oh, they're the same as they were last night, right? Not quite. Almost, but not quite. Here's my diagrammatic representation of a part of the stars that you might see as you look around the universe. Okay? Now, I've only drawn a part of it because if I drew everything, I wouldn't be able to illustrate anything. Okay? So, the kinds of stars that you see overhead, they actually do change a little bit every night. Why do they change? Okay? Here's the Earth. Okay? It's a terrible scale, I know, but anyway. Okay? And because one side is facing the sun and one side is not. Okay? This is the night side and this is the day side. Okay? So fast forward to like 10 o'clock tonight, and we're going to be on this side. And when you look out to see the stars, okay, because the Earth is facing in one direction, which stars will you see? Far out, guys, come on. Which stars will you see? Well, as you look out, right? Let me get another color. You will see a sort of bunch of stars that sort of correspond to here. And if you look sort of further out, I guess the furthest stars you could see would be over there. But obviously you can't see stars that are behind the Earth. Does that make sense? On the opposite side, on the day side, okay? Now, as you guys know, the Earth doesn't sit still in its position around the sun. It moves, it orbits, okay? So it's moving around in this kind of fashion. Okay, again, very realistic, right? So when I go to a different spot, like say here, okay? So again, the Earth got fatter. Anyway, never mind. The night side of the Earth is facing a different direction, right? So I'm going to see different stars, okay? Now, how long does it take to go all the way around back to the start?
365.
Yeah, 365 and a quarter. Actually, it's not quite that, but it's pretty close. Days, right? Day, night cycles, yeah? Okay. So the sailors worked out, okay, look, as you look up, I'm trying to look for some sort of fixed point so I can know where I am, okay? It's almost fixed, but it's not quite. It changes a little bit each night as I look up, right? But when you go about 360 times, 360 nights around, and, you know, journeys along the sea, they do take a long time, right? That's when you get back to the start, and you've got the same set of stars overhead, okay? Now, because this, you know, sailors knew that you've got this orbiting around the sun, okay? They knew they're not just moving in a straight line. The Earth is not moving in a straight line. That's why it comes back to its original position. So they knew that as they change from position to position, it's a rotational change. It's not like sort of the Earth is heading along in a single direction, okay? And that's why the kinds of stars that it can see will be different. They knew it was rotation, so they said, okay, this rotational difference, right? We'll call that our degree. And by the way, degree is just a general word. Like, you know, we use it for all kinds of things, because when things go up a degree, we mean they're increasing, so we use them for temperature as well as for angles. And when they wanted more precision, they just said, well, let's break that up into minute portions, right? Hence minutes, right? Okay. Now, we sort of lucked out, okay, as a planet, because we talked about this. The ratio between how long it takes to go around the sun and how long it takes to spin around, right? It's about 365, okay? So it's pretty close to a nice handy number, okay? But if you're on a different planet, Mercury, Venus, Jupiter, anything, right? The ratio between the rotation and the orbit would be different. So you'd come up with a different number, at least if you were sailing on the oceans of Venus. Nothing else really has oceans. Actually, I think Jupiter has some moons with oceans. But anyway, that's another story. So, but here's the key, okay? This 360 was just lucky. It was just lucky. In fact, it's not really even 360, okay? It was just close enough for sailors to say, all right, that's a good measure, okay? So, this 360 degrees, number one, this is my first reason, it was a lucky measurement from sailors, okay? If we're on another planet, it'd be different, okay? But number two, whose perspective is this measure measured from? Whose perspective? Maybe that's not even a question you think about. It's from the perspective of the sailor, isn't it? The idea is that as you look up at the stars, if you turn your head just a little bit, okay, a degree, okay, that's how much the stars are changing from time to time. So it's from the perspective of an observer, right, watching something that's spinning around and trying to describe that change, okay? Now, for these two reasons, this is why degrees actually do not work very well when you start to do real maths. When you start to do stuff like, say, trig. This is why we're trying to introduce it together with trig and radian measure. Okay, so